Okay, good morning everyone. Thank you, Christios, for your kind introduction. And surely many of you know Professor Bokluda, who also attended the previous two workshops, but he could not come today. Originally the talk was planned to be given by him. And together with our colleagues from the HP Institute in Leoben in Austria, we've been investigating shear mode fatigue crack growth. As we've already seen in some of the previous presentations, it's not that easy to deal with mode 2 and mode 3 given stress intensity factors, but we try to understand the micromechanisms of this crack propagation. And in order to be able to verify some of the models, we need to compare the intrinsic data. So in this talk, I will tell you how the understanding of the intrinsic resistance has progressed. The history of studying of modes 2 and 3 crack propagation is not that rich as that of mode 1. And it is still a challenging problem, and that is mainly caused by the fact that the mode 2 and mode 3 loaded cracks, they do not open. So we have a very large extrinsic part, and we are especially interested in the near threshold region, and there the extrinsic part, so that means the crack closure, is several times higher than the intrinsic one. And there are also some other complications even to design the experimental arrangements for pure mode 2 and pure mode 3 experiments. And also, when we load the crack under mode 2 or 3, it can bifurcate into the opening mode. To start with, let's have a look at the basic dislocation model of fatigue crack propagation. At this first row, we can see the unloaded state. In the second, in the maximum loading, and the last one is after unloading. And in the case of mode 1, we have emission of edge dislocations like this, and we have blunting. And then after unloading, we have a new fracture surface. In the case of mode 2, we have emission of the edge dislocations in this direction. And in this case, we consider an ideal case where the crack plane lies in a slip plane. And also here, after the unloading, some of the dislocations come back and create a new fracture surface. But in the case of mode 3, the screw dislocations only create a step at the edge of the specimen. You can see here in the three-dimensional representation. And in this case, in this ideal case, no mode 3 crack propagation is possible here. But in reality, it is in polycrystalline materials we have different orientations. So we have to consider that some mode 3 crack propagation is possible. But the experimental indication says that it is always lower than mode 2 crack propagation. This is one of the possible explanations how remote mode 3 crack can propagate by segments, by these components of mode 2. So even if there was no pure mode 3 crack propagation, the crack can propagate by local mode 2 or 1 due to the spatial tortuosity of the pre-crack. The other possible way is this model published a long time ago, where the dislocation pileups at particles create decohesion, and then the crack can again propagate by local mode 2. Now this is, we want to have a look at some quantitative description, and this is a connection between experimental and theoretical consideration. According to the emission model, the range of the stress intensity factor at the threshold should be proportional to the product of the modulus and square root of Berger's vector. And we found effective thresholds for mode 1 for a couple of single-phase metallic materials and this equation gave a good results with a good agreement with the measured data. And then we made experiments for mode 2, and we measured the effective thresholds in mode 2. And we use this equation, but it is, of course, here is a shear modulus, but it is modified by this parameter n alpha. It depends on an angle of the deflection of the mode 2 loaded crack. Because if you load the mode 2 a crack in mode 2, and it starts propagating not in the plane, but it deflects by some angle, then you have to consider the local mode 2 stress intensity. And this is in this formula, n alpha parameter. And we found, according to experiments, that the different crystallographic structures of materials have some typical values of the deflection angles. So this is this parameter n alpha, and when we put them in this equation, we have also a good agreement between these calculated values and the measured effective values. For mode 3, due to the reasons I told you, it is more complicated. In mode 3, we don't have any such nice equation, but what we could see from the experiments that the ratio of mode 3 effective threshold and mode 2 effective threshold was approximately the same for the investigated metallic materials. There were 6 of them until now. Now let's move on to some experimental specifications. How could we measure the effective thresholds? We use the cyclic compressive loading for the pre-crack generation at the notch, and after this loading and after unloading, the pre-crack remain slightly open. So in this case, we avoided the closure effects, and we engineered the specimens to eliminate the large plastic zone in order to avoid the effect of it, and we engineered it in vacuum. And then here is a micrograph of such an open pre-crack, and after that we applied the pure mode 2 or pure mode 3 experiment. And after we applied a certain number of loading cycles in the shear mode, we fractured the specimen and we measured the length of the shear mode crack, and we plotted one point at this diagram. So it is 1 point for each specimen. And we could say that if there was no crack propagation, we are below the threshold, and if there was some crack propagation, we are above the threshold. So in this case, by this method, we could measure the effective thresholds, because at the beginning of the experiment, we had really closure-free data. After the crack started propagating in mode 2 or mode 3, then there already some closure occurred, and here we already had some retardation. But for the threshold and the initial direction of the crack propagation, you could consider it as intrinsic behavior. Now let's have a look at the fracture surfaces. We applied stereophotogrammetry. We took the 2 images and rotated the samples and could calculate the 3rd dimension and reconstruct the fracture surfaces in 3 dimensions. And here we can see the mode 1 pre-crack, and this is the area of the mode 2 growth, and then this is the final fracture. And these arrows show they are always parallel to the applied shear direction. And we have an example here for an Amco iron, which is a polycrystalline pure iron, and stainless steel. And we can see that the behavior is completely different. In the case of the Amco iron, we have here facets with some oriented patterns, and the fracture surface is very flat. We have a small deflection angles here. In the case of the austenitic steel, we can see immediate deflection towards the pure mode 1. For mode 3, we have an example of Amco iron and periodic steel, but the situation is in Amco is very similar. We have also these facets and small deflection and twist angles of these facets, so the crack propagated along the shear plane in this case. So it's not always the case that the crack deflects towards the local mode 1. In the periodic steel, which is the cementite laminas. Here already the local mode 1 propagation occurred because the twist angles of these facets are close to theoretical 45 degrees. And we measured the deflection and twist angles for many profiles in different materials. Here you can immediately see what I talk about below the crack by mode 2, and this is the deflection angle. And in the case of mode 3, the twist towards local mode 1 is by this beta. And you can see these being values for the investigated materials. And you can also see the comparison of the effective mode 2 threshold given by the equation I showed you before and the measured value, so you can see a good agreement, and you can see a measured effective mode 3 threshold. For the first three materials, you can see there are large differences between the deflection angles, and it is given by the crystallographic structure of these metals. In the case of the other materials, the crack propagation was very close to local mode 1, and the explanation will come later. So for the first three metals, in the BCC structure there is many slip planes with small angles between them, and it is very easy for the dislocation emission model to find a conveniently oriented slip system and to realize this model with only slight deflection from the shear plane. So we measured a relatively small angle for anti-iron, and we have also preliminary results for niobium, which is also BCC, and we observed the same behavior, small deflections and crack propagation along the shear plane. In the case of titanium, in the HCP, some of the slip systems are more difficult and the angles are higher, so there is medium probability to find the slip planes, and we have larger angles. And in the nickel in FCC, the angles are even larger. There are also 1-1-1 planes, so this angle was the highest one. But still, the oriented patterns and on the facets or on the fracture surfaces, it was the same for all these three materials. On the other materials, we did not see such facets. And in the case of the austenitic steel, we could see that there was a very flat crack that immediately deflected towards local mode 1. And this is probably caused by a different micromechanism occurring there. It is an FCC metal like nickel, but it has stacking faults, and cross slip is not possible there. So it is very difficult to find the conveniently oriented slip systems, and the maneuverability of the dislocation is low. And the model of absorption of dislocations generated inside the material described this behavior, because according to this model, the stress field of the dislocation and the crack tip, when it overlaps, it produces crack extension most effectively under opening mode, because there is a nanoscopic decohesion of the material. In the case of the paralytic steel, the mode 1 growth can be explained by the strong barriers to dislocation movements created by the cementite lamellas, and there is a cleavage between the cementite and ferrite border and cracking of the lamellas, which is also effective under opening mode. And the experimental results from the ferritic steels show that the behavior is similar to that of the paralytic steel and not to the ferritic steel. And so this means that in the paralytic grain, once the mode 1 is triggered, then it continues also in the rest of the material. Okay, to sum up, for the case of mode 2 and mode 3, the crack propagation mechanisms, growth rates, and defective thresholds, they are different. We measured a higher intrinsic threshold for mode 3 than for local mode 2 in all tested materials. There was a formula proposed for intrinsic mode 2 threshold, which is based on the model of omission of dislocations from the crack tip, and it depends on the reflection angles, and it is in a good agreement with the theoretical measured intrinsic mode 2 threshold. In the BCC material, the crack propagated in the original shear plane, and the low deflection angles and the easiness of the slip caused that also the effective threshold was the lowest one in these metals. And the effective threshold mode 1 should be considered with for the materials where we observe the immediate local mode 1 propagation, and so the local mode 1 should be calculated for this deflected crack, and the local mode 1 effective threshold should be considered here.